The static was already there. In 1977, a volunteer scanning a printout of radio telescope data circled 6 characters and wrote one word in the margin. Not a sentence, not a report, one word in pen beside a signal that lasted 72 seconds and was never heard again. The word was wow, and it is still, nearly 50 years later, the closest thing to an answer anyone has ever written down. That is the whole problem, held in a single exclamation point. Not the silence. The fact that we got close enough for someone to reach for a pen. The room is quieter than it was an hour ago. Whatever sounds were filling it, traffic, voices, a television in another room, have settled into something lower, further away. The kind of quiet that arrives without announcement and stays until you notice it. You probably didn't choose to be awake at this hour. Most people don't. This is Sleepy Science Channel, and the thing you're about to sit with for a while is one of the oldest questions anyone has thought to ask. Not the loudest question, not the most dramatic, just the one that keeps coming back, the way something unresolved tends to do at the edge of sleep, when everything else has finally gone still. There are people who have been listening to this channel for a long time now. They show up quietly, the way a light stays on in a window without any announcement. If you're one of them, thank you. That continuity is not something I take for granted. There is a sound under every silence. It has been there since before there were ears to hear it. Tune any radio to a frequency with nothing broadcasting on it, and the hiss that fills the gap is not emptiness. It is information. Some of it is interference, wiring, atmosphere, the low electromagnetic murmur of everything electrical in a mile radius. But some of it, a small and measurable fraction, is something else entirely. Photons that have been travelling since the universe was roughly 300,000 years old, back when it first cooled enough to let light move freely. They are still here, still arriving, still landing in our instruments the way a letter arrives from someone who mailed it before your grandparents were born. That hiss has a name, the cosmic microwave background. It is the oldest light in the universe, stretched by 14 billion years of expansion into the microwave band, into the same frequencies where a radio telescope listens for signals from other civilizations. It is technically always in the room. The people who built those early telescopes knew this. They accounted for it. They subtracted it from their data, set it aside as noise, and pointed their dishes at the stars. The calculation was simple on paper. Somewhere out there, if life had evolved and reached for technology, it would leak. It would broadcast. It would announce itself the way any sufficiently active thing does, not necessarily on purpose, just by existing loudly enough that the evidence escapes into the surrounding space. The question was whether we would recognize it when it arrived. The first serious attempt to answer that question happened in 1960. A radio astronomer named Frank Drake pointed a large dish in West Virginia at 2 nearby stars, Tau Ceti and Epsilon Eridani, and listened for 400 hours over several months. The project was called Ozma, after the queen of a fictional land reachable only by strange and difficult means. He heard nothing he could trust. That result, nothing trustworthy, would repeat itself for the next 6 decades with variations only in the equipment used to reach it. Bigger dishes, more sensitive receivers, broader frequency ranges, better algorithms for separating signal from noise. Each improvement in the tools produced the same fundamental result: a more detailed picture of the silence, more channels listened to, more stars surveyed, more data collected and filed and returned to as the processing power to analyze it improved. And underneath all of it, running like a current through every negative result, the same question the whole enterprise had begun with: what does a signal even look like? How would you know one if you heard it? The 1977 signal, the one that earned its exclamation point, arrived at a telescope in Ohio called Big Ear. It came in at a frequency of 1,420 megahertz, which is significant. That is the frequency at which neutral hydrogen emits radiation, a number that any civilization with basic radio astronomy would know. It had been proposed decades earlier as a kind of universal frequency for interstellar communication, precisely because it is physically meaningful across any chemistry, any origin point, any technology. If you wanted to guess where a stranger might wait, you would guess the place everyone already knows. The signal was strong, narrow band. It rose and fell exactly the way a point source moving through the telescope's field of view should rise and fall. Every characteristic pointed toward something real, and then it was gone. In 30 years of attempts to detect it again, same telescope, same frequency, same coordinates, it never came back. Not once. Which left the people who found it with a question that does not resolve cleanly. Was it something that broadcast once and stopped? Something that moved? Something our instruments happened to catch at exactly the right moment of exactly the right day? Or was it something local, an aircraft, a satellite, a reflection of our own noise bounced off something we did not know was there? Nobody agreed then. Nobody agrees now. The file stays open. There is something quietly strange about sitting with that fact. Not disturbing exactly. Strange in the way that certain distances are strange when you hold them in your mind long enough. Not threatening, just larger than the mind expected. Whatever sent that signal, if anything did, is not waiting for a reply. The time required for a reply to arrive at even the nearest plausible source would be measured in years or decades, depending on where in the sky you think it originated. Any civilization that sent a message in 1977 and has been waiting for a response has been waiting 47 years and counting. Maybe they stopped waiting a long time ago. Maybe they never expected an answer. Maybe the whole concept of waiting and expecting and reaching back is something that only makes sense to creatures whose lives are short enough that 47 years feels like a long time. This is the part that is easy to miss in the louder versions of this question. The one where the focus is all on whether they are out there, on how many, on how far, on what they would look like or want or say. Underneath that question is a quieter one about scale, about what it means to look for something across distances that make a lifetime feel like a rounding error. If you've been lying here wondering what you think the answer is, whether we're alone, whether the silence is real, whether the wow signal was something or nothing, that question is worth keeping. Not because there's a right answer to write down, but because the fact that the question doesn't leave you alone says something about what kind of problem it actually is. If you want to leave a guess somewhere, there's a space for that below this. I find myself reading those sometimes later when the channel is quiet. There is no clean way to begin a story about silence. The silence is the story, or at least a large part of it, and silence does not lend itself to openings or introductions or any of the scaffolding that usually signals that something is beginning. So instead, a number. We have been listening deliberately and with purpose for roughly 60 years. The universe is approximately 13.8 billion years old. What we have covered in time is about 400 millionths of a percent of the available window. We have not been told no. We have barely finished saying hello, an equation with too many empty chairs. In 1961, a small group of scientists gathered at a research facility in Greenbank, West Virginia, to discuss a problem that had no established field, no agreed methodology, and no data. They needed a way to organize their thinking. Frank Drake, who had run Project Ozma the year before and heard nothing he could trust, wrote something on a blackboard before the meeting began. It was not an answer. It was a frame for the question, a way of breaking one impossible problem into several slightly smaller impossible problems and lining them up where everyone could look at them. It became known as the Drake equation. The equation multiplies a series of factors together to estimate the number of civilizations in our galaxy that might be detectable right now. How many stars form per year? What fraction of those stars have planets? What fraction of those planets could support life? What fraction actually develop life? What fraction of life develops intelligence? What fraction of intelligent life develops technology that leaks into space? And finally, how long such a civilization stays detectable before going quiet, through collapse, transcendence, or simple disinterest in broadcasting. Multiply all of those together and you get a number. The problem is that most of the variables are not numbers yet. They are placeholders, hopes dressed up in algebraic notation. Some of the factors have improved since 1961. The fraction of stars with planets, for instance, was a genuine unknown when Drake wrote his equation. Decades of telescope data have since revised it upward dramatically. Most stars, it turns out, have planets. Many of those planets orbit in zones where liquid water is at least theoretically possible. The universe is, by this early measure, far more accommodating than the pessimists expected. But the later terms in the equation, the ones about life, intelligence, technology, longevity, remain almost entirely unanchored. We have exactly one data point for each of them. One planet where life emerged, one species where intelligence followed, one civilization where technology became detectable from space, and one is not enough to calculate a rate. One is not a statistic, one is just an event. The equation has critics. Some argue it creates the illusion of precision around things that are genuinely unknown, that writing variables in a row on a blackboard makes the problem feel more tractable than it actually is. Others argue the opposite, that the equation's value was never in producing a number, but in clarifying exactly where the uncertainty lives. You can agree on the structure of the question, even when you cannot agree on any of the answers. What happens when you plug in optimistic values, the numbers you'd expect from a scientist who believes life is abundant, intelligence is common, and civilizations tend to survive themselves, is that the galaxy fills up quickly. Hundreds of thousands of detectable civilizations, perhaps millions, distributed across the spiral arms, each one a potential source of the signal nobody has found yet. What happens when you plug in cautious values? the numbers from someone who thinks the emergence of life is staggeringly improbable, that intelligence is a near accident, that civilizations are brief and self-terminating, is that the expected number drops below 1. The most likely outcome on those inputs is that we are alone, not just in our neighborhood, in the entire observable galaxy. Both sets of inputs fit the available evidence. Both are defensible. The equation cannot tell you which set is right because the equation is not doing science. It is doing philosophy with a veneer of mathematics over the top. This is not a criticism of Drake or of the equation. It was never meant to give an answer. It was meant to show that the question had structure, that it could be divided, that different people could disagree about different parts rather than talking past each other about the whole. By that measure, it has worked extraordinarily well. 60 years of argument about the search for extraterrestrial intelligence has been, in large part, argument about specific terms in a specific equation that one scientist wrote on a blackboard before a meeting because he needed to organize his thoughts. The empty chairs around the table, the variables that remain blank, or nearly blank, are where all the interesting uncertainty lives. Take the last term, the average length of time a detectable civilization stays detectable. Drake himself, when he first ran the numbers, used 10,000 years as a rough estimate. Some researchers use 1 million. Some, looking at the trajectory of human civilization's relationship with its own technology, use 200. That single variable, slid from one end of its plausible range to the other, moves the expected number of civilizations from an almost impossible solitude to a crowded galaxy and back again. One unknown, one variable with no measured value doing most of the work. The universe doesn't offer this kind of variable without irony. The term that most determines whether we are alone is the one that measures how long a civilization like ours tends to last. There is a version of the Drake equation that people sometimes run informally, at night, when the math becomes less about astronomy and more about something harder to name. You take the optimistic inputs, you get the large number, you look up at a sky that holds that number of minds and you ask why none of them have made themselves known, and then you switch to the cautious inputs, and you watch the number fall, and you try to decide which result is more troubling, the silence of an absent crowd or the silence of one. Neither answer resolves cleanly. That is the honest situation. The equation was always more useful as a mirror than as a telescope. What you see in it depends on what you bring to it, and what most people bring, whether they admit it or not, is a need for the answer to go one particular way. Drake himself, in later interviews, tended toward optimism. He believed the galaxy was full. He thought the silence was a temporary condition, a function of how recently we had started listening and how crude our instruments still were relative to the problem's scale. He held that position with the particular patience of someone who had spent his career listening to a question rather than expecting an answer. The equation still sits in the middle of the field like furniture nobody has moved. Not because it is answered, but because no one has found a better way to arrange the uncertainty. Somewhere in that arrangement of unknowns is a chair that represents you, the listener, the civilization, the one data point the equation has to work with. One chair occupied, the rest empty, the math refusing to say whether that's unusual or expected or somewhere in between. It is possible to sit in that chair for a very long time and feel both things at once. that the silence means nothing and that it means everything, and that the equation was never going to tell you which. 60 years of pointing a dish at silence. The dish at Greenbank, West Virginia, is 85 feet across. In 1960, it was the instrument Frank Drake used to listen to two stars for 400 hours over several months. It was motorized to track a target as the Earth rotated, which was a relatively new capability at the time. It was also, by modern standards, an almost comically limited tool for the task, like pressing a glass to the wall of a house the size of the Milky Way. Drake heard nothing he could trust. He filed the result. He moved on to the next thing, and in doing so, he set a pattern that would define the entire field for the next 6 decades. Methodical, patient, largely unrewarded, and constitutionally incapable of giving up. The history of SETI, the search for extraterrestrial intelligence, is mostly a history of improved equipment producing the same fundamental result. Each generation of instruments could hear further, resolve finer distinctions, process more data. Each generation produced a silence that was quieter than the previous silence, which sounds like progress, and in one narrow sense is, but does not change the essential situation. In 1974, a message was sent, not received. The Arecibo telescope in Puerto Rico broadcast a sequence of 1,679 binary digits toward a globular cluster 25,000 light-years away. The message was designed to be decodable. Its length is the product of 2 prime numbers. Its content includes basic mathematical and biological information about the species that sent it. The cluster it was aimed at will not receive it for 25,000 years. If anyone there responds immediately, the reply arrives in 50,000 years. This is sometimes described as humanity's introduction to the cosmos. It is more precisely described as a note slid under a door that nobody will open for longer than our species has existed in its current form. The WOW signal arrived 3 years later, in 1977, through a telescope in Ohio called Big Ear. It has been covered at length in the chapter before this one, so what matters here is less the signal itself than what happened afterward. For 30 years, researchers returned to the same frequency, the same coordinates, and found nothing. The signal was not repeated. It was not explained. It was logged, preserved, and argued about, and it remains the single most compelling unresolved detection in the history of the search. Everything after it has been a quieter version of the same weight. The late 1970s and 1980s brought larger surveys, wider frequency coverage, and the beginning of what would eventually become systematic rather than targeted searches. Rather than pointing at one star and listening, researchers began developing systems that could sweep large portions of the sky across multiple frequencies simultaneously. The technical challenge was not pointing the dish, it was handling the data, separating genuine signals of interest from the relentless background of terrestrial interference, satellite transmissions, aircraft, and the natural radio emissions of various astrophysical objects that have nothing to do with intelligence. In 1992, NASA funded a major search program, the most ambitious to date. It was cancelled by Congress 1 year later after a senator described it on the floor as a search for little green men. The funding disappeared. The researchers regrouped under private support, renamed the effort the SETI Institute, and continued working with reduced resources and no federal backing. The Phoenix Project, which ran through the 1990s and into the early 2000s, observed roughly 1,000 nearby Sun-like stars across a range of microwave frequencies. It used some of the largest radio telescopes in the world, including Arecibo during observation windows. It found no confirmed signals. Its results were negative in the careful scientific meaning of that word. The search was real. The methodology was sound. The data was analyzed rigorously. And the conclusion was that none of the targeted stars produced a detectable signal matching the search parameters. This is the texture of the field. Careful, expensive, negative, continued. The Allen Telescope Array, a project backed partly by Microsoft co-founder Paul Allen, was designed from the ground up as a dedicated SETI instrument, not a general-purpose telescope that SETI researchers borrowed time on, but an array of small dishes built specifically to run ongoing searches while also doing conventional radio astronomy. It came online in a limited form in 2007. It ran into funding difficulties. It was partially shut down in 2011. It resumed operations under new funding. This pattern, capability, shortfall, adaptation, continuation, has repeated throughout the field's history with a regularity that almost resembles its own signal. In 2015, a major private initiative called Breakthrough Listen was announced, backed by $100 million in funding from a Russian-Israeli entrepreneur named Yuri Milner. It is the largest SETI effort in history by funding, and it brought access to some of the world's best telescopes, including the Green Bank telescope, a successor in the same West Virginia location to the original 85-foot dish where Drake began. By 2020, Breakthrough Listen had published multiple data releases covering millions of stars, billions of frequency channels, and a volume of data that would have been unprocessable in any previous era of the search. The result remains, at the time of this recording, unresolved, which is not the same as negative. It is more accurate to say the search at this scale has been running for a handful of years, and a handful of years is not a verdict. 60 years of this. Patient, meticulous, technically improving, spiritually unresolved. The people who have spent careers in this field tend to share a particular quality, an ability to hold a very long view of time and to find something other than despair in the absence of an answer. Drake was that way. Jill Tarter, who ran SETI Institute research for decades and inspired the character Ellie Arroway in Carl Sagan's novel Contact, spoke often about the scale of what had actually been searched. One glass of water drawn from the whole ocean. The question was not whether fish exist. The question was whether this particular glass contained one. She thought the metaphor was useful. She thought the search had barely started. Whether that patience is scientifically justified or philosophically necessary, or simply the only available response to a problem that will outlast everyone currently working on it, that is harder to say. The dishes keep turning. The data keeps coming. The silence keeps being sorted through, carefully, looking for the sound under the sound. What a civilization sounds like from very far away. A civilization announces itself mostly by accident. Think about what Earth looks like from 10 light-years away, from the neighborhood of Epsilon Eridani, one of the 2 stars Drake pointed his dish at in 1960. An instrument sensitive enough would detect a planet in a temperate orbit, orbiting a yellow star, with an atmosphere that contains oxygen in quantities that simple geology cannot explain. Oxygen is chemically reactive. Left alone, it bonds with rock, with iron, with organic matter disappears. An atmosphere with free oxygen in it requires something producing oxygen continuously at a rate faster than it can be absorbed. On Earth, that something is photosynthesis. Life. This is what an atmosphere can say without anyone intending it to say anything. The biosignature, a chemical imbalance that requires biology to maintain, is a leak, not a broadcast, not a message, a consequence of existing at sufficient scale for long enough that the evidence escapes. A civilization adds more leaks, nitrogen compounds from industrial agriculture, chlorofluorocarbons from refrigerants, compounds that have no natural geological source, that appear nowhere in the universe without a factory. The electromagnetic smear of radio and television broadcasts, escaping through the atmosphere and moving outward at the speed of light in an expanding sphere. A faint thermal excess, waste heat from energy use. The atmospheric signature of combustion from 10 light-years away, with an instrument we do not yet have. Earth is not invisible. It is merely difficult to read. The question of what to look for, how to recognize a civilization that may not know or care that it's being observed, is one of the most genuinely open problems in the search. Most early SETI work focused on deliberate signals, a civilization choosing to broadcast, choosing a frequency, constructing a message. This is a reasonable place to start, but it carries an assumption that is worth examining. It assumes that a civilization capable of interstellar communication would choose to make itself findable. It assumes the intent to be heard. Not all communication requires that intent. The expanding radiosphere around Earth, the wavefront of human broadcasting moving outward at light speed, is now roughly 100 light-years in radius. Inside that sphere, any sufficiently sensitive instrument pointed at our Sun would detect an anomalous electromagnetic environment, not necessarily decodable, not necessarily identifiable as intelligent in origin, but anomalous, different from what a bare, lifeless planet produces, different in ways that physics alone cannot account for. This leakage is what most researchers now consider the most realistic detection scenario. Not a beacon, not a deliberate hello, but an unintentional signature. The exhaust of a civilization that is too busy existing to send messages but is detectable anyway. The way a city is visible from orbit at night without anyone having turned the lights on for the purpose of being seen. The instruments required to detect such a leakage across interstellar distances are not things we currently possess. The radio leakage from a civilization like ours, at the distances involved, drops off with the square of distance. By the time it reaches even the nearest stars, it is faint enough that our best current telescopes could not detect the equivalent of our own broadcasts from 4 light-years away. What we can detect from neighbouring stars is a strong and deliberately constructed signal, something pointed at us on purpose. The accidental signature requires better instruments than we have built. This is not an argument against looking. It is an argument about what kind of looking is available to us now versus what kind might become available with more advanced technology. The gap between the signal we could detect today and the signal that an average technological civilization might actually be producing is a gap that may close with time. The Square Kilometre Array, a radio telescope project spanning multiple continents and currently being built in South Africa and Australia, will be significantly more sensitive than its predecessors. Future space-based interferometry projects could extend that sensitivity further. But the more fundamental question, what does a civilization actually sound like? What does it leak? What does it announce without meaning to? That question depends on assumptions about what other civilizations are doing with their energy, their atmosphere, and their electromagnetic environment. There is a classification system proposed by a Soviet astrophysicist named Nikolai Kardashev in 1964 that organizes civilizations by energy use. A Type 1 civilization uses energy at the scale of its home planet. A Type 2 harnesses the full output of its star. A Type 3 controls the energy of its entire galaxy. Earth is currently somewhere below Type 1. We use a fraction of the solar energy available to us and almost none of the rest. A Type 2 civilization, by definition, is doing something dramatic enough with its star that the consequences are measurable from outside. A structure built around a star to capture its full output, sometimes called a Dyson sphere, after physicist Freeman Dyson, who proposed the idea, would not look like a star. It would look like a point source of infrared radiation at a temperature corresponding to the structure's outer surface, without the visible light signature of a bare stellar surface. An anomaly, something that physics does not produce on its own. Researchers have looked. The Kepler Space Telescope, during its planet-hunting mission, produced light curves for hundreds of thousands of stars, graphs of stellar brightness over time that reveal planets passing in front of their stars as tiny, periodic dips. In 2015, one star produced a light curve that no natural explanation has fully accounted for. The star, catalogued as KIC 8462852 and informally named Tabby's star after the astronomer who drew attention to it, dimmed in irregular asymmetric patterns, not like a planet, not like a binary companion, not like any standard astrophysical phenomenon. The most exotic explanation was an alien megastructure in partial construction. The explanation that eventually gained the most traction was a swarm of dust and cometary fragments. The mystery has not completely resolved. The star still behaves strangely. What this episode demonstrates is less about aliens than about how the search works in practice. A genuine anomaly appears. Researchers take it seriously. Mundane explanations are tested against the data. The extraordinary explanation is kept on the table, but not treated as preferred. The anomaly narrows. It is probably dust, but does not fully close. File stays open. This is the scientific method doing its job in a domain where the stakes are unusually high and the data is unusually sparse. There is no rush to claim a detection, because a false positive in this field carries costs that outweigh the attention it generates. The SETI community has a protocol for candidate signals, a careful series of verification steps, independent confirmation attempts, and deliberate restraint in public communication. Precisely because the history of premature excitement in this field is long, and the credibility costs are real. There is something else worth sitting with here, which is the list of things we have decided to look for, and the things that list leaves out. We search for radio signals because radio is what we know how to make and detect. We look for atmospheric biosignatures because we know what biology does to an atmosphere when biology is made of the same things we are made of. We look for anomalous stellar light curves because we have built instruments that record stellar light curves. Every search parameter is a projection of what we know onto what we are trying to find. A civilization that uses quantum communication channels, or that modulates neutrinos, or that has found some physics we have not yet formulated. That civilization is invisible to us not because of distance, but because of conceptual distance. We do not have the vocabulary. This is not a counsel of despair. It is a reminder that the search is also a self-portrait. The closer you look at the list of things we're willing to call evidence, the more it resembles a description of ourselves, which may be the only honest place to start. You look for what you know. You refine the instruments. You expand the vocabulary as the instruments improve and the physics develops. And somewhere in that list of things we have decided to look for, and all the things it does not yet include, is a civilization producing a signature we have not thought to search for, in a language we have not learned to read, announcing itself the only way physics allows, by existing loudly enough that the evidence escapes. The filter. No one agreed to walk through. Somewhere between a planet with the right chemistry and a species capable of building a radio telescope, something happens. Or many things happen. Or one thing happens once, and that changes everything. Nobody agrees on this. Nobody has agreed on it since the idea was first proposed, and the disagreement is not a failure of the field. It is the honest shape of the problem. The concept has a name, the Great Filter. It was formalized by an economist named Robin Hanson in 1998, though the idea had been circulating in various forms for decades. The argument is simple. If life and intelligence are common, the galaxy should be full. It is not obviously full. Something filters out the progression from simple chemistry to detectable civilization. That filter exists somewhere along the chain. The question is where. Hanson's framing splits the problem into two regions, behind us and ahead of us. If the great filter is behind us, if we have already passed through the hard part, that the most likely culprit is something in the early stages of life's development. The origin of life itself, perhaps. The specific conditions under which self-replicating chemistry first emerges are so demanding that they occur only rarely, across cosmic timescales, in the right kind of molecular environment. Or the emergence of the eukaryotic cell, the kind of complex nucleus-containing cell that all multicellular life on Earth is built from, which seems to have appeared exactly once in Earth's history, through a specific and unusual merger between two very different kinds of microorganisms, or the origin of sexual reproduction, which dramatically accelerates evolutionary change but is not an obvious or inevitable development. Any of these steps, if they are genuinely improbable, rather than likely given enough time, could be the filter. And if the filter is behind us, the implications are actually reassuring in a cold way. It means we made it through. It means intelligence, wherever it arises, tends to persist. It means the quiet sky is a function of rarity, not danger. If the filter is ahead of us, the implications run in the other direction. A filter ahead means something awaits every civilization that reaches our level of technological development, something that terminates or silences them before they become detectable, or shortly after. The candidates include the obvious ones: nuclear war, engineered pandemics, climate collapse, artificial intelligence misaligned with biological survival, some combination of self-inflicted catastrophes that advanced technology makes available at a scale biology cannot absorb. But they also include the less obvious ones. Civilizations that develop technology and then deliberately choose silence, not because they are afraid, but because broadcasting turns out on reflection to be inadvisable. civilizations that transition into a form of existence that does not produce detectable electromagnetic emissions, that go digital, go inward, lose interest in the physical universe as an arena of activity. Civilizations that simply spread slowly, or not at all, because the distances involved make expansion impractical across biological timescales. The filter ahead does not have to be catastrophic. It could be a transition. It could be a choice. It could be that what we would recognize as a civilization is a phase, a brief, loud, messy phase between simple life and something quieter and harder to detect. The reason this framing unsettles people is what it implies about the Fermi Paradox's resolution. If advanced civilizations are common and the filter is ahead, we should expect to join the filtered. This silence is not evidence that they are absent. It is evidence of what happens to them. And if we can look around at our current situation, at the range of self-terminating technologies we have developed within a century of building our first radio telescope, and wonder whether we are in the process of demonstrating exactly what the filter does, that wondering does not come with a comfortable resolution. This is the version of the argument nobody likes to say out loud first in a room full of people. There is a third position that does not fit neatly into Hanson's binary, which is that the filter is distributed, not one barrier, not a catastrophic threshold ahead. A long series of improbable steps, each one individually plausible, collectively rare enough that the product of all of them is a number far below 1 per galaxy. Life arises rarely. Complex life arises rarely from simple life. Intelligence arises rarely from complex life. Technology arises rarely from intelligence. Each transition is possible but not likely. The universe is old enough and large enough that you still get some outcomes, but not many. This version of the filter is harder to visualize than the others. It does not have a single dramatic cause or a single sobering implication. It has many quiet causes and a cumulative implication that what we are is not the expected result of a common process, but an unusual product of a long improbability, which is either humbling or clarifying depending on how you hold it. What the great filter actually is, where it actually sits, is still unknown. The field has not converged on an answer. The honest position is that we have one civilization in the sample, ours, and one civilization is not enough to calculate a rate of filter passage. We cannot tell from a single example whether we are typical or exceptional. We cannot tell whether the step we're standing on was the hard part or the easy part. All we can say with confidence is that something thins the progression. The sky is quiet enough that something must. And the most important question, whether the difficult thing is behind us or ahead, is one that the sky, for now, is not answering. Every reason we might be the first. Start with a moon, not any moon, a large one, unusually large for a planet of Earth size, sitting at a distance and mass that produces a stabilizing effect on the planet's axial tilt. Without it, or something like it, the axial wobble over long timescales would be dramatic. Swings of tens of degrees rather than the small oscillation Earth currently experiences. The climate consequences of that wobble, across millions of years, are difficult to fully model, but are generally considered unfavourable to the sustained development of complex life. Stable seasons, stable enough that ecosystems can adapt and persist, rather than being periodically scrambled by new climatic regimes. That stability, at least in part, traces back to something we sometimes call just the moon, as if it were ordinary. It is not obviously ordinary. The leading model for how it formed requires a specific impact. A Mars-sized object striking early Earth at a specific angle, with a specific momentum, early enough in the solar system's development that the debris could coalesce into the right configuration. Change the size or timing or angle of that impact, and you get a different moon, or no moon, or something that does not produce the same stabilizing effect. The collision happened once, by apparent chance, and the consequences are still unfolding. This is the structure of the argument that Earth might be genuinely rare, not mystical, not triumphalist, just a list of things that happened, each one individually possible, collectively unusual. Plate tectonics, the movement of crustal plates that recycles carbon from the atmosphere through the rocks and back out through volcanic activity, maintaining a rough equilibrium that keeps the planet's temperature within the range where water stays liquid. Mars, as far as we can determine, does not have active plate tectonics. Venus does not appear to have a functioning carbon cycle of the kind Earth does. Of the rocky planets in our solar system, the one with the right combination of interior heat, crustal structure, and cycling chemistry is, so far, the one with the life on it. The Sun, a comparatively stable star, G-type, middle-aged, without the violent flaring behavior of the smaller, more common red dwarf stars that dominate the galaxy. Red dwarfs are interesting candidates for hosting life because they are so abundant and so long-lived, but they present challenges. Their habitable zones are close in, which means planets in those zones may be tidally locked, and their early lives are characterized by intense flaring that may strip planetary atmospheres. Whether life can establish itself under those conditions is genuinely unknown. The Sun, by contrast, has been a stable and relatively benign energy source for the 4 billion years it took Earth to go from simple chemistry to radio telescopes. Jupiter, a gas giant sitting in the outer solar system, large enough that its gravitational influence has spent billions of years deflecting or capturing objects that would otherwise have continued inward toward the inner planets at a much higher rate. The role of Jupiter as a partial shield against comet bombardment has been debated, and the current scientific picture is more complicated than the simple "Jupiter protects Earth" framing that circulated widely in the 1990s. Jupiter may also have sent additional comets inward in earlier periods, but the gravitational architecture of the solar system, the specific arrangement of giant planets in the outer system and rocky planets in the inner system, is a configuration that planet-finding missions have suggested may be less common than was once assumed. Stack these: a moon with the right mass, a star with the right stability profile, a carbon cycle with the right chemistry, an outer solar system architecture with the right gravitational balance, a distance from the galactic centre that sits in a region with reasonable metal abundance, but not so close to the centre that radiation environments become hostile, a timing that puts the development of complex life after the galaxy has had enough generations of stars to produce the heavy elements biology requires, but while the Sun is still in a stable phase. Each one is not a miracle. Each one is something that happens, somewhere, sometimes. The question is the product of all of them. How often do all of these conditions occur simultaneously, in the same system, at the right time, in the right sequence? That product is unknown. That product is, in some sense, the whole question. A hypothesis called the rare earth hypothesis, put forward in a book by paleontologist Peter Ward and astronomer Joe Kirschvink in 2000, assemble this kind of argument into a systematic case. Their contention was that the conditions necessary for complex multicellular life are so specific that simple microbial life might be fairly common in the universe, while complex life, the kind that builds telescopes and asks questions, is vanishingly rare, perhaps unique. The hypothesis has critics. One response is that the factors listed as requirements for complex life on Earth may not all be actual requirements, that life is more adaptable than the rare Earth framework assumes, that the conditions identified as necessary are identified as such because they are what we know, not because they are actually limiting. Another response is that even if the product of all those factors is very small, the number of planets in the observable universe is very large, and a very small probability applied to a very large number of opportunities can still produce a substantial expected count. Both responses are reasonable. Neither is a resolution. What the rare earth argument does that is useful is shift the weight of the question. The default assumption in SETI's early decades was that life was common, that intelligence was a natural product of evolution given time and stable conditions, and that the silence was therefore puzzling. If instead the conditions for complex life are highly specific, if what we represent is not the expected outcome of a routine process but an unusual configuration of many unlikely things, then the silence is not a puzzle. It is what you would expect. Empty chairs are normal. We are the exception. There is something neither comforting nor disturbing about this framing. It makes us significant in the sense of being unusual, without making us significant in any other way. The universe does not arrange itself around our existence. It simply happened to produce us once through a long series of chances, and the fact that it did so does not require or imply that it did so elsewhere. The last thing worth sitting with in this chapter is a question the rare earth hypothesis raises without quite answering. If we are the first, what comes with that? Not responsibility necessarily, not mission. Those framings impose a moral structure on a physical fact which may not be warranted, but something, an awareness that whatever developed intelligence is, whatever allows a collection of atoms to sit up and wonder about the rest of the universe, it is, on this account, new. We are not inheriting something. We are beginning something that has not been done in this galaxy before, or has been done so rarely that the distinction barely matters. That is a different way of holding the question than the one that expects an answer to come back from the sky. And it is a possibility the data does not rule out, a universe that forgot to wait for us. Consider two civilizations. Each one rises on a rocky planet orbiting a stable star. Each one develops language, then writing, then mathematics, then physics, then radio technology. Each one eventually builds a dish and points it at the sky. Between these two events, the first civilization's radio hello and the second civilization's radio hello, lies 1,000 light years of space. They never meet. They never hear each other. Not because of distance, because of time. The universe is not synchronized. There is no shared present across cosmological distances, no moment at which everything is simultaneously at the same stage of development. A star that formed 2 billion years earlier than our Sun in a region of the galaxy where the heavy elements were already abundant enough to build rocky planets, has had 2 billion extra years. The civilization that might have risen around such a star, if it rose, if it persisted, if it went through the same or analogous sequence of steps, had 2 billion years more to evolve, to build, to transform, to go quiet. 2 billion years is a span so large that the words are approximately meaningless. Anatomically, modern humans have existed for roughly 300,000 years. Complex animal life on Earth goes back about 600 million years. 2 billion years ago, the most complex life on this planet was microbial mats. Whatever rose and fell in that span, around stars that formed 2 billion years before ours, would be unrecognizable in every direction. This is the temporal dimension of the Fermi Paradox, and it gets less attention than the spatial one. The question, where is everybody, is usually imagined as a spatial problem, a matter of distance, signal strength, and the geometry of how far a broadcast can travel. But it is equally a temporal problem. 2 civilizations could exist in perfect radio range of each other and never overlap by millions of years. They could each broadcast a signal that crosses the other's planet in sequence, separated by enough time that neither one is still listening. The universe spent most of its first billion years without the heavy elements needed for rocky planets and carbon chemistry. The first stars were enormous, short-lived, and composed almost entirely of hydrogen and helium. They burned fast and died in supernovae, seeding the galaxy with heavier elements that subsequent stellar generations incorporated. Planets like Earth could not form until there was enough carbon, oxygen, iron, and silicon available, which required several generations of stellar deaths. This means the timeline for life as we know it has a hard lower bound, not from the Big Bang. From some later point when the chemical prerequisites existed, and the distribution of stars across the galaxy by age is not uniform. Some regions formed stars earlier, some later. The timescales for life's emergence, intelligence's rise, and technology's development vary depending on which star, which planet, which location in the galactic disk or halo you're discussing. There is a concept sometimes called the galactic habitable zone, a band of the Milky Way, neither too close to the violent centre, nor too far from the metal-rich disk, where conditions for complex life are most favourable, and where rocky planets have been forming long enough for evolutionary timescales to play out. Earth sits in this zone. The zone is real. What it implies is a concentration of opportunity in space, and a range of timing in when that opportunity became available. Within the galactic habitable zone, the distribution of civilizations in time might look like a bell curve, a wave, or a cluster, depending on how you model the inputs. The important implication is that the wave is not narrow. The range of possible moments for a technological civilization to arise, even within favorable conditions, spans billions of years. The overlap between 2 specific moments within that range, for 2 civilizations separated by interstellar distance, might be vanishingly brief even if both civilizations exist. This gives the silence a different texture, not the silence of absence, the silence of non-overlap. Picture it in compression, the entire history of the universe reduced to a single year. The Big Bang happens on January 1st. Earth forms around September 2nd. Complex animal life appears in mid-November. Humans emerge December 31st around 11 p.m. Radio technology appears in the last seconds of the year, the window in which a civilization broadcasts detectable radio signals and simultaneously has the technology to detect others may be brief, measured, in some pessimistic accounts, in centuries. Scaled to the cosmic year, that is a fraction of a second. Two such windows, separated by 1,000 light-years, have to coincide within the same fraction of a second for their signals to cross, while anyone is still listening. The chance of that coincidence, given the full range of cosmic time, is very small. And yet, if the window is not centuries but millions of years, if civilizations, once they arise, tend to persist in some form indefinitely, the picture changes. The overlap becomes more likely. The silence reasserts itself as a genuine puzzle. The resolution depends entirely on how long technological civilizations last, which is the variable nobody has measured, and which is the most important term in the whole equation. There is a subtler version of the timing problem that operates at shorter scales. Even civilizations that exist at the same cosmic moment are not necessarily broadcasting at the same cosmic moment. The history of Earth's radio leakage into space is roughly 100 years long. Before 1900, we were electromagnetically invisible. No detectable radio signature, nothing that would distinguish our planet from a lifeless rock at radio frequencies. In the next few centuries, it is possible that our broadcast profile will change dramatically. Higher frequency communications, fiber optics, directional signals that leak less into space. Our window of unintentional radio visibility may be a blip even within our own civilization's history. If other civilizations follow similar arcs, loud for a period, then quieter as their technology matures, the timing problem compounds. Not only must they exist at the right cosmic moment, they must be in the loud phase of their development during the brief window that overlaps with our ability to listen. This is not an argument that they are absent. It is an argument that the expected signal is rare, not because civilizations are rare, but because the right moment to hear them is rare. We may not be alone so much as early or late, or simply offbeat. The universe is not arranged for simultaneity. It does not synchronize its civilizations or stagger them at convenient listening intervals. It produces them when conditions allow, in whatever configuration probability generates, across a time scale that makes human history a rounding error. In that context, the silence of 60 years of listening is not a verdict. It is a sample. The universe's answer to the question of whether we are alone is being computed across billions of years of stellar evolution, planetary formation, biological development, and civilizational timing, and it has been running far longer than we have been listening. The result, if it comes, will arrive in its own time, not ours. Quiet is not the same as empty. There is a game theorist's version of the Fermi Paradox that does not require any of the usual explanations. No great filter, no timing misalignment, no rare earth, no search limitations, just a simple, stark observation. If you are intelligent enough to build a radio telescope, you are also intelligent enough to reason about what happens when you use it to announce your location to the rest of the universe. And reasoning about that, carefully and without optimism, might lead you to go very quiet. The argument is sometimes called the dark forest theory, after a framing in a science fiction novel by the Chinese author Liu Cixin, though the underlying logic predates that name by several decades, and exists in academic literature under more clinical headings. The core of it is this: any civilization with the technological capacity to receive a signal also has, at some point, the technological capacity to do something about it. The universe does not come with guarantees about what kind of civilization you might reach, and a civilization that broadcasts its location is betting that every entity capable of hearing it is friendly, or at least indifferent. That is a bet that only has to go wrong once. The game theoretic logic runs like this. Civilizations have resource needs. Resources are finite. Two civilizations in contact across interstellar distances have imperfect information about each other's intentions. They cannot communicate fast enough to build trust before either one might have the capacity to act. The asymmetry of the situation favours preemption for a sufficiently paranoid or sufficiently rational actor. The cost of not acting against a potentially hostile civilization is potentially catastrophic. The cost of acting against a potentially friendly civilization is the loss of something that might have been valuable. Under those conditions, a civilization reasoning about the mathematics of survival might conclude that the correct strategy is silence, not passive silence, absence from the electromagnetic landscape, removal of detectable signatures, active measures to avoid announcement, and then, potentially, observation, listening for the locations of others, building a map of what is out there, and making decisions that are not audible to the targets of those decisions. This is not necessarily what the universe looks like. It is what the universe could look like if the logic of self-preservation, applied rigorously by a sufficient number of civilizations, converges on a particular equilibrium. That equilibrium is a silent galaxy, not because no one is there, but because everyone capable of reasoning about the stakes has reasoned themselves into quietness. There are counter-arguments. One is that civilizations capable of interstellar communication might also have ethical frameworks that make preemptive action unacceptable, that what we project onto aliens when we imagine them playing zero-sum resource games is a specific and perhaps parochial view of intelligence's moral development. Another is that a galaxy-spanning civilization, if one exists, has access to so much that any individual planet's resources would be negligible. The economics that drive competition in scarcity might not apply at that scale. Both counter-arguments are reasonable, neither is decisive. We do not know what intelligence produces morally or economically at scales we have not reached. We are reasoning from a sample of one, and one is not enough to generalize. What makes the dark forest hypothesis particularly difficult to dismiss is that it requires no new physics, no exotic explanations, no filters or rare conditions. It requires only that some civilizations are cautious, and that caution, under the relevant conditions, is rational. The silence of the sky becomes not evidence of emptiness, but evidence of strategy. There is a thought experiment that follows from this. If the dark forest equilibrium holds, if the sky is quiet because intelligent life has learned to be quiet, then our century of radio broadcasting has already done what the cautious civilizations chose not to do. The sphere of our electromagnetic signature, now 100 light-years in radius, has already reached several thousand stars. If anyone was listening, and anyone is now making a decision based on what they heard, that decision is being made, has been made, somewhere in the dark. We do not know the answer yet because the distances involved mean we would not receive any consequence for decades or centuries at minimum. We are in the period before the reply, if there is one. We are in the quiet between the question and whatever comes next. It is worth sitting with the fact that this is the one explanation for the Fermi Paradox that is directly disturbing rather than merely unsettling. The others, rarity, timing, search limitations, early emergence, are all forms of loneliness, or of patience, or of humility about our instruments. The dark forest is a different thing. It is an argument that the silence might be not just an absence but an active condition, that the sky is not empty but disciplined, that what we hear when we listen is not nothing but the sound of things choosing not to be heard. Whether that is what the sky actually contains, that is the question the evidence does not yet resolve. The sky is quiet. There are two different reasons silence can be quiet. Only one of them is the comfortable one. The bias built into every search we've run. Every search begins with a guess about what it is looking for. That guess determines which instruments get built, which frequencies get monitored, which planets get prioritized, which signatures get counted as evidence and which get filed as noise. The guess is not arbitrary. It is built from the best available knowledge about what produces life and intelligence and detectable technology. But it is still a guess, and any search shaped by a guess will find what the guess prepared it to find, and miss what the guess did not prepare it to see. The search for extraterrestrial intelligence is the most ambitious search in the history of science. It is also, in a structural sense, the most constrained, not by resources or instruments, but by imagination. We are looking through a keyhole shaped exactly like ourselves. Start with radio. The decision to search for radio signals made sense in 1960. Radio was the technology Drake knew how to use. The frequencies around 1420 MHz, the hydrogen line, were proposed as a logical meeting point because hydrogen is the most abundant element in the universe, and any civilization with basic radio astronomy would know it. These are not arbitrary choices. They are reasonable inferences from known physics about where a deliberate signal might be placed. But they carry an assumption that another civilization chose to signal in the same medium and near the same frequencies that a 1960-era human radio astronomer would choose to look. That a civilization that may be millions of years more technologically advanced than us has, for reasons of its own, decided to use radio. Not laser pulses, not neutrino modulation, not gravitational wave encoding, not something that emerges from physics we have not yet formulated. A civilization that has moved beyond radio, the way we have mostly moved beyond Morse code, would not be visible to a radio telescope even if it were broadcasting continuously in every direction. Not because it is trying to hide, simply because it is using a different door, and we are standing at the one we know how to open. This problem has a name in the literature, the SETI assumption, or more broadly, the assumption of communicative behavior. We are looking for civilizations that want to communicate, that have the technology to do so in ways we can detect, and that have chosen to use that technology in the directions we happen to be looking at the moments we happen to be observing. Any search parameter that assumes intentional communication is also assuming a particular set of choices that a civilization we know nothing about may not have made. The alternative approach, looking for unintentional signatures, is subject to a different but related bias. We look for atmospheric biosignatures using oxygen and methane and nitrogen compounds, because those are the outputs of life as we know it. Made from chemistry, we know. We look for thermal anomalies and industrial pollutants because those are what our civilization produces. We look for megastructures around stars because Freeman Dyson imagined a specific engineering solution to a specific energy problem using physics that applies to our civilization. All of this is reasonable. All of it is also narrow. Life that does not use oxygen metabolism is invisible to a search for oxygen. Intelligence built on chemistry we have not imagined is invisible to a search for our chemistry. Technology that exploits physical principles we have not discovered is invisible to a search through the lens of what we have discovered. There is a concept sometimes called the SETI paradox. The most advanced civilizations would be the hardest to detect. A civilization that has fully optimized its energy use produces less waste heat, not more. A civilization that has mastered communication produces tightly directed signals, not omnidirectional broadcasts. A civilization that has learned to engineer at fine scales might not produce the large physical signatures we associate with advanced technology. In this framing, the civilizations we could most easily detect are young and inefficient. Civilizations at roughly our stage of development, leaking energy and radiation in all directions because they have not yet figured out how to be precise, which means the search, even if it is perfectly executed, may be preferentially sensitive to civilizations at exactly our level of development, in exactly the brief period when they look like we look now. A more advanced civilization might be effectively invisible to us, not because it is trying to hide, but because advancement, in the direction of efficiency and precision, reduces the very signatures we are looking for. The bias also operates in time and space in more mundane ways. We search stars within a certain distance because those are the ones our instruments can resolve. We prioritize Sun-like stars because Earth orbits one, and Earth is the only planet we know to have produced life. We focus on the galactic disk and deprioritize the galactic halo, where stars are older and more metal-poor. We observe during windows determined by telescopes, scheduling, and funding cycles, rather than by any logic intrinsic to the search. None of these decisions is wrong. All of them reflect real operational constraints and reasonable defaults, but they collectively define a search space that is not the whole space. They define a particular neighborhood of the universe, a particular frequency range, a particular model of what advanced life looks like, and they search that neighborhood thoroughly without it being the only neighborhood. What this adds up to is not an argument that the search is futile or misdirected. It is a reminder that a null result, finding nothing in the search space, does not mean nothing exists in the space that was not searched. We have not found nothing. We have found the edges of our own imagination clearly mapped and carefully explored, and the territory beyond those edges remains as unknown as it was before we began. The history of science is full of searches that found nothing until the instruments changed. Bacteria were invisible before the microscope. Radio waves were invisible before the first antenna. Gravitational waves were invisible until we built an instrument sensitive enough to detect a space-time ripple produced by two black holes merging 1 billion light-years away. The invisibility in each case was a property of the instrument, not the thing. The history of SETI may follow the same arc. The silence we have recorded so far may be the silence of instruments still being built, vocabularies still being assembled, keyhole apertures slowly widening toward the shape of whatever is actually out there. We have not found nothing. We have found the edges of our own imagination, and the search for what lies beyond them is just beginning to have the tools it needs. A number that was never about aliens at all. 60 years. Hold that number for a moment without attaching it to anything. Not to radio telescopes or frequency ranges or the names of projects and programs. Just 60 years as a span of human time. What it looks like lived. 3 or 4 full careers. A childhood to an old age. The gap between a parent's birth and a grandchild's graduation. A period short enough that many people currently alive have lived through all of it. Now hold it against a different number. 13.8 billion years. The approximate age of the observable universe. Not the age of the Milky Way. Not the age of the sun. The age of everything we can see and most of what we cannot. The age of the background hiss in every radio receiver. The age of the light that the cosmic microwave background has been carrying since before there were any stars. 60 years into 13.8 billion. 400 millionths of a percent. A fraction so small it requires scientific notation to write correctly and resists honest comprehension even when written correctly. We have been listening for 400 millionths of a percent of the available time and are drawing conclusions from the silence. This is not a comfortable thought if you came here expecting resolution. It is, in its way, more unsettling than most of the other ideas in this series, because it doesn't resolve toward aliens or toward solitude. It resolves toward patience, which is harder. Patience without an end point. Patience with something that may not be answerable in any human lifetime or any number of human lifetimes. But there is something else in that number if you hold it differently. Something that is not about aliens at all. The search for extraterrestrial intelligence is, at its most honest, a mirror. Every question it raises loops back to the same object. Us. How long do civilizations last? How often does intelligence emerge? What does a technological species do with its technology? Does it build or destroy? Reach outward or collapse inward? Is the silence a sign that what we are doing now is typical or terminal? Is intelligence in the universe mostly a brief phase? Or can it persist? Every version of the Fermi Paradox's resolution says something about what we might be. The Great Filter says we are either exceptional survivors or approaching a threshold. The Rare Earth says we are an unusual configuration of common ingredients. The Dark Forest says we are broadcasting into a silence that may be strategic. The timing mismatch says we are early or late, or out of phase with whoever else is out there. None of these answers is about them, not really. They are about us, wearing the shape of a question about the sky. This is not a criticism of the search. The search is real and valuable, and has produced genuine science along the way. Improvements in signal processing, in telescope design, in the understanding of planetary atmospheres and stellar variability, in the development of astrobiology as a serious discipline. The search has earned its place in the history of science, not by finding what it was looking for, but by refining the question, until the question itself became clearer. And the question, made clearer, is something like this. Under what conditions does the universe produce beings capable of asking about themselves and the universe they inhabit, and what happens to these beings. That question does not require aliens to be answerable. It begins to be answerable through physics, through evolutionary biology, through the history of Earth's complexity, through cosmology, through the science of planetary systems and stellar evolution. The search for extraterrestrial intelligence is one line of inquiry into that question, the one that looks outward for a second data point. But the question exists independent of whether the second data point ever arrives. There is a long tradition in science of questions that reoriented the people who asked them long before they produced an answer. Copernicus did not immediately change how people lived. The shift from Earth-centered to Sun-centered cosmology took more than a century to fully propagate through European thought, and it produced not just a new astronomy, but a new relationship between humans and the cosmos they inhabited, a relationship in which the centrality of Earth was no longer assumed, in which the universe did not arrange itself around human observation. Darwin's insight did something similar to biology. Not just a new mechanism for the origin of species, but a new understanding of what humans are in relation to other living things. Continuous, not separate, built by the same process, subject to the same pressures. The search for extraterrestrial intelligence carries a similar potential. If it finds something, the reorientation is obvious and enormous. A second data point for intelligence, a confirmation that what we are is not unique, a universe that suddenly contains company. But even if it finds nothing, the sustained act of looking, the serious, funded, methodical practice of asking whether we are alone, has already begun a reorientation. It places humanity inside a question rather than outside it. It treats the existence of other minds as something to investigate rather than something to assume or deny. That is not nothing. That may, in the long run, be the most important thing the search produces regardless of what it finds. What do you do with a question that might not be answerable in your lifetime? This is not a rhetorical question. It is the actual situation the search for extraterrestrial intelligence presents to the people who care about it. The distances and timescales involved mean that even if a signal were detected tomorrow, even if verification were immediate and clear, the question of what the signal means, where it comes from, what sent it, and what comes next would unfold across decades or centuries of analysis. The answer to the question of whether we are alone might arrive in fragments, over generations, without a single definitive moment of clarity. This is also, in a broader sense, the situation that science presents to anyone who takes it seriously. Most of the important questions are not answerable in a lifetime. The people who built the instruments that eventually detected gravitational waves had been dead for decades before the signal arrived. The people who developed the mathematics of general relativity did not live to see it confirmed by GPS satellites. Science inherits across generations. The question belongs to everyone who asks it, not just to whoever happens to be alive when the answer comes. The 60 years of SETI are a first chapter. If it finds something, the reorientation is obvious and enormous, a second data point for intelligence, a confirmation that what we are is not unique, a universe that suddenly contains company. But even if it finds nothing, the sustained act of looking, the serious, funded, methodical practice of asking whether we are alone, has already begun a reorientation. It places humanity inside a question rather than outside it. It treats the existence of other minds as something to investigate rather than something to assume or deny. That is not nothing. That may, in the long run, be the most important thing the search produces regardless of what it finds. What do you do with a question that might not be answerable in your lifetime? This is not a rhetorical question. It is the actual situation the search for extraterrestrial intelligence presents to the people who care about it. The distances and timescales involved mean that even if a signal were detected tomorrow, even if verification were immediate and clear, the question of what the signal means, where it comes from, what sent it, and what comes next would unfold across decades or centuries of analysis. The answer to the question of whether we are alone might arrive in fragments, over generations, without a single definitive moment of clarity. This is also, in a broader sense, the situation that science presents to anyone who takes it seriously. Most of the important questions are not answerable in a lifetime. The people who built the instruments that eventually detected gravitational waves had been dead for decades before the signal arrived. The people who developed the mathematics of general relativity did not live to see it confirmed by GPS satellites. Science inherits across generations. The question belongs to everyone who asks it, not just to whoever happens to be alive when the answer comes. The 60 years of SETI are a first chapter, not a first chapter in the narrative sense, with a setup and a rising action and a conflict moving toward resolution. A first chapter in the scientific sense. The initial framing of the question, the development of the first instruments, the accumulation of the first data, the discovery of the first constraints. 60 years from now, the search will have different instruments and different vocabulary and, possibly, different results. 100 years from now, the same. The question will still be here. The hiss under every silence is still playing. It was playing before the first radio telescope was built, before the first question about other minds in the sky was seriously asked, before the particular arrangement of matter that became you assembled itself out of ingredients cooked in the cores of long-dead stars. It will be playing after everything now listening has gone quiet. That continuity is not comforting in the way a resolution is comforting. It does not close anything. It simply places the 60 years, the dishes and the data and the one exclamation point in a margin in 1977, inside a frame so much larger than itself that the frame becomes the point. We have not been told no. We have only just started asking. The answer, if there is one, was never going to arrive this early. Whatever is in the silence, company or solitude, discipline or absence, a signal waiting to be recognized or a confirmation of an aloneness that turns out not to be the worst thing, it will still be there tomorrow night, and the night after, and the night after that, for as long as there are ears pressing toward the dark. For now, it is enough to have asked. For now, sleep.